Good afternoon, all of you.
Good afternoon,
Good
sir.
afternoon, sir.
Good afternoon, sir.
Good
Good afternoon,
afternoon.
sir.
I want to talk to Yash regarding attendance record. Yash, are you there? No, who is other CR of the class?
Sir, I am the CR.
Okay. Uh, are you keeping record of attendance regularly?
सर वो एक्सटेंशन ना यश ने डाउनलोड की हुई है तो वही करता है.
तो यश और आप एक बार मुझे उसका कंसोलिडेटेड, आई वांट कंसोलिडेटेड अटेंडेंस टिल नाउ, जितना भी अभी तक लेक्चर्स हुए हैं डेट वाइज. डेट वाइज फर्स्ट यू अरेंज all the roll numbers in a sequence.
Yes, sir.
एक्सेल फाइल में उसको पेस्ट कर दीजिए और उसके ऊपर एक डेट्स डाल के और नीचे फिर उसमें पीपी करके पूरा एक कंसोलिडेटेड एक्सेल शीट आई वांट.
Okay, sir.
Because within few days we'll be releasing one circular which will show the name of students जिनका attendance short है.
Okay, sir.
And it is announcement for you, all of you, that you should be very regular in attending your classes, whatever class it is. है ना, सभी classes में you should be regular. Half of the semester is almost over and half से भी ज़्यादा semester over है. If I remember correctly, then you have your end semester exams from second week of March. Am I right? Exact date you can tell if you know.
सर 14 से है शायद.
14 से हैं, तो इसका मतलब हुआ कि टुडे इज 8th, तो नॉट मोर देन you can say roughly 1 month time is left. So 4 weeks time we have. So be very particular. एक class test भी आपका होना है, that will be in first week of March. So prepare for that. And we have 4 units to cover. Then we are doing fiber optics. After this we have electrodynamics unit on electricity and magnetism, superconductivity, then we have quantum mechanics. So these are the chapters which we will be doing. So we have 4 units to complete and we have only 4 weeks time, so we have to speed up a bit. Okay, so let us start with today's lecture. It is we discussed yesterday some basics involved in propagation of light through any medium, and the most important light propagation is total internal reflection, because this is the key of propagation of light through optical fiber. Or we also say that principle of propagation of light through optical fiber is total internal reflection. So we should understand what this is. We discussed this yesterday, that whenever light is coming, yes, I have not shared my screen.
आपकी आवाज क्लियर नहीं आ रही.
सभी को क्लियर नहीं आ रही है कि सिर्फ कुछ लोगों को ये प्रॉब्लम है?
सर आ रही है.
आ रही है सर.
ओके, हाउ मेनी ऑफ, चलो जिनको आ रही है वो ठीक है, बट वो बता सकते हैं जिनको नहीं आ रही है. दे कैन unmute and tell me that my voice is not audible or it is not clearly audible. तो सिर्फ अगर किसी एक दो के लिए प्रॉब्लम हो रहा है तो आप अपना नेटवर्क यू सी, है ना, यू शुड बी इन ए एरिया वेयर सिग्नल इज स्ट्रॉन्ग. ओके, सो as I was saying that this total internal reflection is important because this is principle of propagation of light through optical fiber. Yesterday we said that whenever light is traveling through denser medium and it strikes the interface where there is change in medium from denser to rarer, optically rarer medium. Then we discuss three things. If this light is incident on the interface at 0 degree angle of incidence, then it goes undeflected without bending. Though there is change in speed of this light, but there is no change in the path of the light. It goes undeflected along the straight line. But when this light ray is incident at some angle theta with respect to the normal, it bends. And we see two things. Partially it is transmitted to the rarer medium and partially it is reflected back. And the strength of the signal or strength of the light which is reflected back in the same medium, that increases with increase in angle of incidence of this light. And then we see that at this particular angle, we go on increasing angle of incidence of this light ray, and when it becomes or equals to theta c or phi c, which is called critical angle, which depends on refractive indices of the two media. Okay, so it depends on this ratio, that is n2 over n1. n2 is refractive index of the rarer medium and n1 is the refractive index of the denser medium. So whenever sine inverse n2 over n1, this is the angle of incidence of this ray, then we see that the refracted ray, it starts grazing the interface, or it makes angle 90 with the normal. From this we get this condition for total internal reflection. We see this angle, it depends on n2 over n1 or refractive index of the rarer. So this is condition for, and further we increase this angle greater than this critical angle, then we see only reflected ray in the same medium. So this phenomena is called what it is called total internal reflection. And this happens at angle greater than the critical angle, and critical angle is what it is. This is how we find critical angle. We can find critical angle for any combination of media like water, glass, air, water, air, for any, because we know what we know, refractive indices. So we can see what should be the critical angle for that interface. So we decide what is the critical angle, and if we make light incident from the denser side at angle greater than the critical angle, then we can see this phenomena of total internal reflection. But if the light ray makes angle less than the critical angle at the interface, then that light is not totally reflected. It is refracted. It goes to the other medium as well. So basic principle of optical fiber is total internal reflection. So we have to see conditions, or we have to make conditions where total internal reflection takes place, so that we can allow, or we can make a condition where light propagates through the optical fiber. There is one very small interesting experiment which you should try at your home if you have, if you can arrange these things to see total internal reflection, because we talk about total internal reflection and it is never observed, because you cannot see light and then you cannot see whether it is totally reflected or it is refracted as well. So for that we do this very beautiful experiment. In this you can see we have this rectangular container. This is big container, rectangular container filled with water. And inside this container I have semicircular glass disc. This is any, you can take any glass, but it should be semicircular in shape. Okay, and then we make light incident on this. We can vary inclination of this, or we can rotate this. It is freely movable, and we can move this disc or this semicircular glass, so that we can vary angle made by, this is the interface, this is interface between glass and water, and at this interface where light is incident, we can see that the normal, the ray makes some angle with the normal. And by rotating this disc or rotating this semicircular glass, we can vary the angle of incidence, and we try to make this angle of incidence greater than the critical angle for glass water interface. Okay, so we are rotating this semicircular glass, and we know what is refractive index of glass, we know what is refractive index of water, though there will be impurities in this water, so refractive index also varies with the contamination of water, but roughly we know what is the refractive index. Then we can find what should be the critical angle. So at what angle we should make this laser incident at the interface, or what angle this laser light should make with the normal and this. One thing you can see that it is going undeflected from here, because as the angle of incidence is zero here, because and with the normal it is making zero angle. Okay, so then you can see that this goes, because this is a laser light, you can see well collimated path of this, and it goes, it gets totally reflected, and total internal reflection happens here, and then you can see light bending like this and going away. So this is, and you can add some color to this water so that you can see very beautiful image or colorful image of this laser beam bending from the interface. You'll see no light here, no laser beam in this direction, and totally it is reflected to this. So you should try this at home. I'm not saying don't try it at home. You should try this at home. If it is possible, you can arrange these things. Okay, then we have another experiment which was demonstrated way back in 1843 by Daniel, and he demonstrated how light can be guided through jet of water. So here in this experimental setup, this is again, we have container which is filled with water. At the base of this container, there is small hole through which water jet comes out. And we can launch well collimated beam, or we can launch laser light through this, or they used some monochromatic source of light, and they used and they propagated it through this jet of water. And what is happening when it strikes water air interface, total internal reflection condition is fulfilled, and it is totally reflected, or it moves through this jet because of multiple successive total internal reflections. So this motivated people that light can be guided through material which is having a refractive index more than air. Okay, so this is very beautiful experiment. Then we have graded index medium. Index is refractive index, and if medium or material medium is having a uniform refractive index, there is no change in refractive index of the medium. As we know that we have, suppose I have this as this is my glass slab, refractive index of this remains same throughout its length. So this refractive index is constant, and light travels within this material of constant refractive index along a straight line. There will be no change in velocity of this light ray, and path will remain straight. As soon as there is change in refractive index, then it bends away. But this is not a graded index. This is what this is. There is step index type of combination, because here there is change in refractive index is abrupt. It is in a step, because a refractive index of this material is, you can say, some n1, and it remains N1 up to here, and then there is abrupt change in refractive index and it becomes equal to refractive index of air, and then it remains again constant. So there is a change, and there is at a single point, and there is a finite change in the refractive index of the medium. But graded index medium is the medium where refractive index is not constant throughout the medium, but it is function of R, that is function of distance. So it is like what? It is like we have the same type of material, rectangular material, but in this material, if we have different regions divided by these layers, and refractive index varies gradually as we move upwards. So that means refractive index varies with this R, this distance here. You can say that at the base, refractive index is maximum, then it decreases layer by layer, and then you can see that light ray which will travel through such medium, which is graded index, where the refractive index is function of R. It will not travel a straight line path, but it will travel a curved path like this. Because at every time it will cross the layer from denser to the rarer, it will get, there will be bending of light. So continuously it is bending. So they are very close layers, and you can say that there is continuous bending of this light as we are moving, or as light is moving from most dense part of this medium to the relatively small refractive index part of this medium. So this is graded index medium, and due to this graded index type of medium, you see mirage formation in deserts. So in that case, what happens, you know that refractive index is also function of temperature. For hot, or you can say for gases, refractive index of gases that varies with temperature. So it is, as it is function of temperature, and then we can say that refractive index will be different for the different regions of this air medium at different temperatures. Okay, and then you can see what? You can see continuous bending of light. As light bends continuously, then this is due to this type of medium that is called graded index medium. Why we are discussing this in so detail? Because this is also what we will see in optical fiber. We have two type of optical fibers. We have graded index optical fibers, and we have also step index optical fibers. So we'll see this effect there as well, and due to this effect, how we can transmit our signal, that we'll also discuss in detail. Then another phenomena you have seen, that is dispersion of light. This we are discussing because this is also due to what? Due to refractive index. The refractive index of the medium is different for different wavelengths. So that's why I'm showing it to you here, that why it is important to send light of monochromatic light through the optical fiber. Otherwise, optical fiber, refractive index, same optical fiber, but for different wavelengths, it will offer different refractive index. As you see in case of prism, there is dispersion of light. You see different colors, because different colors, they bend by different degree as they move through the same refractive index, but it is refractive index is not same, it is different for different wavelengths. So there is Cauchy's formula, which there is inverse relation between wavelength and the refractive index. This much you should understand. So that now let us start with this chapter. These are the basics which you already know, and just to refresh these basics and give you a little more idea how we'll be using these basics in discussing optical fiber. So we have communication. We want to send signal from one point of the space to the other point, and that we do we have different communication systems. We send signal either in the form of, we can send it in any form. We can send signal like electrical signal. So for that, you need some waveguide through which this electrical signal will be moving. So we generally say that conductors are, they allow easy path for flow of current. So electrical signal can be sent easily through copper wires, through aluminum wires. But here we are talking about communication of, now we have carrier waves. Our carrier waves are light waves. We have made this optical fiber, and through this optical fiber we can send light signal. And the most this reliable communication system is where we can send signal quickest and in the fastest way. So electromagnetic waves, their speed is 3 into 10 raised to power 8 meter per second through vacuum, and it gets reduced, as we saw. It depends on the refractive index of that medium, and it gets n times reduced in that medium of refractive index n. So most reliable, economical and fastest way of communication is electromagnetic system or electromagnetic waves. We should know 3 things when we talk about any communication system. That is source of information, or the information, how, in what form information is available with us, which we want to transmit or we want to send. Another thing is through what medium or through what channel we will be transmitting this signal. And the final thing is the receiver, where we receive this signal. So we are interested in sending signal. We can send it like the crudest way, or सबसे पुरानी बात करें, we go back, then we can say that by simply fire को burn करके भी हम signal, we can send signal. We are sending signal through open environment medium, and it is light signal again, or smoke, or anything you can produce, and that is coded signal. You can code, you can say that if we produce fire, that means this, and if we produce smoke, that is this. So we are coding, this is coding, and we are sending this signal from one point to the other point at far distance. Okay, so but now technologically we are sound, and we can do this in a better way. And the better way is that we should choose a better source of light. So we choose laser light, which we have done laser. They without losing their intensity, they travel large distances. Then it is also important what should be the channel, or what should be the medium, what should be the guide through which we should send this signal. And this is what we'll be discussing in this unit, in this section, and that is optical fiber. We have electromagnetic wave. We know how to code information on this electromagnetic wave, or using this electromagnetic wave. And we have the receiving end, where we detect this electromagnetic wave. We have technology for that, but we do not have technology to transmit this signal from source to destination or the receiver. And that is done when we invented optical fiber. So let us see, these are different communication systems. As I said, that we have electrical lines, we have through atmosphere, we send radio signals, and then we have optical fiber, and this is the channel through which we send light waves, and with minimum distortion, we get a light at the receiving end. So, how this optical fiber, invention of optical fiber, this has revolutionized the field of communication. We long distance communication में प्रॉब्लम था. अगर आप तो नहीं कभी किया, ट्रंक कॉल्स बुक किया करते थे हम लोग, तो ट्रंक कॉल बुक करने में अब तो लैंडलाइन भी नहीं है, तो देयर वर डिफिकल्टीज इन सेंडिंग सिग्नल, है ना, वो कभी आपसे डिटेल में विल टॉक अबाउट दैट. So optical fiber has wide applications in telecommunication, and not only in telecommunication, it has in medicine, in automotive industries, बहुत जगहों पे, अलग-अलग जगहों पे there is application of this optical fiber. Laser operations we talk about. So optical signal we send through these optical fibers. और ऑप्टिकल फाइबर आपके बॉडी में डाल के we can locate exactly where we want to operate or whatever. So there was the main thing is what? It is the capacity, how much signal we can send through these optical fibers. So due to this revolution, due to discovery of, or due to invention of this optical fiber, we say that we can achieve the capacity of sending signal, and this is increased to 10 billion digital bits can be transmitted per second through optical fibers. By this, what we mean, if I say that we have this is my optical fiber. I am interested in sending a digital signal. I code that digital signal in the form of pulses from laser source. This is my laser source. It produces one pulse of light, then it stops. It produces another pulse, then again it stops, then it produces another pulse of laser. So these are pulses, laser pulses. And digitally, how we code this signal, we say that pulse means 1 and no pulse means 0. Then again we have laser light of this intensity. Light is showing intensity here. Then you have 0. So this is my coded signal, which I'm interested in sending through this optical fiber. So what is the rate of sending such signal? What is the capacity of sending? So I can say that in 1 second duration, I have produced these pulses, 1, 2, 3, 4, 5, 6 pulses of laser. And 12-bit is the data information. It is in 1010101010. So if this is the capacity, so that means 12 bits per second is the capacity of this or sending. And you can even see the duration of time. It will be very small. In 1 second, we are producing 12 bits. So that means you can see that what will be the duration between these 2 bits. That will be 1 by 12 second. Okay. So what I'm saying, what we are claiming here, or what is achieved today, it is 10 billion. We can send 10 billion such bits, digital bits per second through optical fiber. I'm not talking about 12, it is 10 billion digital bits per second can be sent through this optical fiber. So this is the capacity of your optical fiber to carry information signal. And this can be further increased to trillions of bits per second by just refining optical fiber along with this with development in lasers, where we have pulsed laser and duration between the 2 pulses is nanoseconds or less than that. So we can have more number of and this signal, and there should be capacity to send such signal or transmit such signal through this. So optical fiber plays that role. Not only optical fiber, but we should be able to produce such at such high rate pulses of laser. So for that, laser development in laser field is also required, and by doing both things we can make communication more and more advanced and fast. Now let us this is all basic, this is all so actually what we are interested in is understanding structure of our optical fiber, then how light propagates through this optical fiber. We'll be discussing different type of optical fibers, and finally we'll be talking about losses in optical fiber, and we'll be talking about applications of this optical fiber in sensors, in telecommunication, and in medicine, and in industry, etc. So let me tell you, as I have already told you, that principle of propagation of light through optical fiber is total internal reflection. So here you can see this is, or let me just tell you what this optical fiber is, or what is the structure of optical fiber. You can see here these are two coaxial cylinders. This inner coaxial cylinder is called core part of optical fiber, and the outer cylindrical part is called cladding. दोनों सेम मटेरियल से बनते हैं, सिलिका से बनेंगे with some oxide doped or some doped with some impurities. Why we dope them with impurities? Just to make a change in refractive index, and just to have different refractive indices. So we have inner part of this optical fiber. It is cylindrical in shape, and refractive index of this inner part is N1. We denote it generally by N1, and we have the outer cylindrical part of this optical fiber whose refractive index is N2, and N1 is always greater than N2. So means core is that part of the optical fiber, or is the innermost part of the optical fiber having more refractive index than the outer part. Okay, ये स्ट्रक्चर है. इसके चारों तरफ भी और भी स्ट्रक्चर है. We have another cylinder around this, which is made up of material which protects it from environmental effects. ठीक है, physical damages and environmental effects like scratch कोई नहीं आना चाहिए, scratch नहीं आना चाहिए, तो इसको हमने this is called buffer, or this is called sheath. So we are protecting our inner core cladding part from physical damages like scratch, some breaking, or all that, and we are also protecting it from environmental effects, moisture, some contamination through environment, or some other effects like temperature and etc. So we place this core plus cladding inside this sheath. Okay, diameter, this is very thin, this optical fiber. We are showing it here. This is size of this optical fiber, or the size of the innermost part of the optical fiber, which is called core, is of the order of, it is 8.5 micrometer is the diameter. So you can imagine this to 62.5. It ranges diameter from 8.5 micrometer to 62.5 micrometer. So you can imagine what is micrometer size, and diameter of this order, micrometer order, means it is very thin. And the outer part, that is core, that is also having diameter in this range only, or order, that is in micrometer. It is greater than this, and diameter of this diameter, that is core, sorry, cladding, this diameter is 125, of the order of 125 micrometer. और sheath इसके बाहर होगा. We need not to know what is the diameter of sheath. Okay, so now how light propagates through this optical fiber. As I said, that total internal reflection is the principle of propagation of light through the optical fiber. So it propagates through multiple successive total internal reflections. So that means when light is launched into the optical fiber from here, from outside, so this diameter is very small, so it is difficult to launch light, but suppose we succeed in launching it, then it travels through the core, and at core cladding interface, it fulfills the condition of total internal reflection. And then it is reflected. Angle of incidence is always equal to angle of reflection. So that means angle here is also equal to what? It is equal to this angle, this angle. So total internal reflection जब यहाँ पे fulfill हो गया ये critical angle से ज़्यादा है, तो this is also more than critical angle. So every time when it strikes the core cladding interface, it strikes at the same angle given ray. So then it propagates through multiple total internal reflections from one end of the optical fiber to the other end of the optical fiber. Okay, so this is how light propagates through the optical fiber. To sum up, I can say that core is the innermost part of the optical fiber, which is light carrying member of the optical fiber. Light कहाँ पे है? You can see cladding में कोई light नहीं है. It is only travels through the core. So importance of core is what? It is that light travels through this core through total internal reflections, multiple total internal reflections. Then we have outer part, which is cladding, and importance of cladding is it helps in confining the light within the core region. क्योंकि total internal reflection कब होगा? जब the total internal reflection होगा जब core cladding interface या refractive index of core and cladding both plays role. So this confines the light within. And then we have the outermost part. As I said already, it is to protect this optical fiber. Now, we can see here in this diagram, because we can launch light at any angle to this into this optical fiber, but it is not always that light will propagate through the optical fiber. Some rays are accepted by the optical fiber, or they travel through through these multiple total internal reflections, and some they leak out of the core and they go into cladding and then move out. So to explain all this, let us see this. This is, I've made 4 different diagrams for you. How light, we can launch light through the optical fiber. This is the case, this is case 1. And in this you can see that we have a ray 1, and it is made incident on the, you can see this is cross section of the optical fiber, and we are launching this from here having refractive index n0 into core having refractive index n1. And this is normal to ear core interface, and light is along this normal, or you can say that angle of incidence for this ray is 0. So it goes undeflected into the core and it moves along the axis of the core. So this is the simplest thing and difficult to do. And this is called, this ray which travels through the axis of the optical fiber is called axial ray. And importance of this is because it takes the smallest time to travel from one end of the optical fiber to the other end of the optical fiber. Okay, so one of the paths which light will follow when it moves through the optical fiber is the axis of the optical fiber, and that ray is called axial ray. And importance of this is that delta t, that is time duration between launching and receiving at the other end, is minimum in this case for this axial ray. T is t minimum, or delta t is minimum. Then we have another way of propagating light or launching light into the optical fiber, and this is we are making a light incident at any angle. We have chosen this ray which is making, this is axis of the optical fiber, and this is my ray R2, and this is making some angle theta with the normal. This is the normal to air core interface. So it is launched at theta angle and it bends towards the normal. This is my normal, towards the normal, because it is going from rarer medium to denser medium N1. And then it strikes at the core cladding interface at some angle theta or phi. And angle made by this, because this is refraction, as it is bending here. This is the refraction, so this is theta I and this is theta R. And I can see what is the relation between theta R and theta I using Snell's law. I apply Snell's law here. I can write that N naught sine of theta I should be equal to N1 sine of theta R. Okay, and if this ray, after striking this core cladding interface, it moves like this. So that means this is where total internal reflection starts. Okay, so then this angle is what it is called critical angle. Okay, means it is incident at core cladding interface at the angle which is just required for total internal reflection. It is at phi c, and then this angle of incidence is called acceptance angle. Okay, because this is accepted by the optical fiber. It travels through the optical fiber. Okay, so we have discussed two cases, and in this case, time taken by, let me write it here. I'll explain this in more detail to you in coming part of the lecture or in coming lectures, but I'm writing it here. The time taken by this ray to move from one end of the optical fiber to the other end of the optical fiber is maximum. Okay. Now let us discuss case 3. This is case 2. And let us discuss case 3. What is case 3? Here we have, this is a ray 2, this ray 2, which strikes the core cladding interface at angle phi c, which is required, minimum angle required for total internal reflection. This is N2 divided by N1. And for all other angles phi greater than this phi c, total internal reflection happens. So total internal reflection is observed for phi greater than phi c, for all angles greater, phi angles greater than phi c. Okay, so let us choose one more ray. This is my ray R3, which I'm making incident at angle greater than this angle. This is, I said that this is theta A. This is what? This is angle of acceptance. When this angle at the core cladding interface is critical angle for core cladding interface, then angle of the ray which we are launching in the optical fiber, and this is what it is, acceptance angle theta A. Okay, so this is my ray R2, which is incident at angle theta A, that means acceptance angle, and this is ray R3, which is incident at angle greater than acceptance angle. And we see that when it strikes this blue colored ray, you see it strikes the core cladding interface, then this makes angle here less than the critical angle. This is my critical angle, and this angle is what it is, less than this phi c. As this is less than phi c, so total internal reflection is not fulfilled and it leaks out of the optical fiber. Okay, so this means that this ray is not accepted by the optical fiber, or it will not be totally reflected within the core, and we lose this signal. Then we have fourth case, case 4, and this case is when we make light incident. This is my ray 4 now. Ray 2 is same, which is at angle, incident at angle equal to acceptance angle. If any ray makes angle less than the acceptance angle, this R4 is making angle less than the acceptance angle, then you can see that it strikes the core cladding interface at angle greater than this critical angle. As phi is greater than critical angle, total internal reflection is possible, or it happens, and then it propagates to the optical fiber. Okay, so this means what is our conclusion when we see all these 4 cases? That whenever total internal reflection condition is just fulfilled, means angle made by the ray at core cladding interface is phi c, then angle of incidence is called acceptance angle. And for angles less than this acceptance angle, or rays which are incident or which are launched through the optical fiber at angle less than this acceptance angle, they are accepted by the optical fiber, and the rays which makes angle greater than the theta A, they are not accepted by the optical fiber. So this angle is acceptance angle. जितनी भी रेज इससे कम एंगल बनाएंगी वो सारी टोटल इंटरनल रिफ्लेक्शन फुलफिल करेंगी, दे विल मूव थ्रू द ऑप्टिकल फाइबर, एंड रेज making angle bigger than this R2 ray, they'll not be launched, or total internal reflection will not happen for those rays, and they will leak out of the optical fiber. So I can draw what? I can draw number of rays. I can say that this is also theta A, हर एक direction से you can draw, and you can draw this cone, and within this cone, whatever ray is made incident on the optical fiber, that is accepted by the optical fiber. So we have defined this theta A. This is acceptance angle, and we have also defined acceptance cone. This is acceptance cone. So this cone, whatever light is incident here on this cone, then that gets propagated. इस cone के बाहर से कोई ray आएगा like this, that is not accepted by the optical fiber. You can see here, this is my cone, and this ray is not within the cone, this R3, but here you can see this is cone of acceptance, this is cone of acceptance, and this is within the cone, this R4, and this is accepted by the optical fiber. Okay, so this is what we have. This is R2, which is just accepted by the optical fiber, which just fulfills the condition of total internal reflection. Anything making angle less than this R4 is easily accepted by the optical fiber. It fulfills the condition of total internal reflection. And any ray which is made incident at angle greater than this R2, that is not accepted by the optical fiber. That will not fulfill the condition of total internal reflection, and that will leak out of the optical fiber. Okay, so now focus on this ray, that is R4, which is accepted by the optical fiber and which moves through the optical fiber through multiple successive total internal reflections. I can write Snell's law for this. We can say that when ray 2 strikes the air core interface, then it goes from there is change in refractive index from 1. I can write Snell's law. Snell's law for ray 2, and this is when we launch it, it is n0 sine of theta a. This is launched at angle which is acceptance angle, is equals to n1. It goes into medium n1 having refractive index n1 sine of angle made by this with the normal, this ray when it enters the core. This is theta r, and when this is phi c, I can call it theta c. This is theta c, because this ray which is incident at theta a acceptance angle, this just fulfills the condition of total internal reflection, and angle made by this at the core cladding interface is phi c, and corresponding angle made by this ray with the axis is called theta c. Okay, and now I can write, because I know from this, if you see this triangle, small triangle here, in which we have theta c angle and we have phi c, and this is 90-degree angle. So I can write using this simple geometry. I can write that n1 sine of theta c can be written in terms of phi c. So I write it as 90 minus phi c. Is n0, this is right and left hand side is same, it is theta a. Or I can write that this is n1 cos of phi c, and phi c is what? It is critical angle. So we know that when ray is launched at angle this, that is acceptance angle, it makes angle at the core cladding interface equals to critical angle. And we have definition from a definition of critical angle. We all know that sine of critical angle, sine of phi c, is equals to a refractive index of rarer medium divided by refractive index of denser medium. Okay, so that means I can replace this cos phi c, or I can write it in terms of sine. So I can write that a relation between 2 is sine square phi c plus cos square phi c is equals to 1, and I can write then cos phi c is equals to 1 minus sine square phi c whole under root. And I can use n2 over n1 in place of sine phi c. So I can write that cos of phi c is equals to 1 minus n2 square divided by n1 square, or taking LCM, I can write n1 square minus n2 square whole divided by n1 square, and under root of that. So I can write it at like this. Okay, so and if I shift this to here, so I can write that n1 times cos phi c is under root n1 square minus n2 square. So I can rewrite my relation using this as sine, this is n0 sine theta a is equals to under root n1 square minus n2 square. And what is n naught? We can write this as sine theta a equals to under root n1 square minus n2 square divided by, I have n naught from here. And what is this n naught? This n naught is refractive index of air. And refractive index of air, we can take this as 1. So I can write that sine theta a is under root n1 square minus n2 square, and sine of angle of acceptance, this is called numerical aperture. This is numerical aperture, which is physically, it means light gathering ability of optical fiber. So from this we can conclude that light gathering ability of optical fiber is independent of dimensions of the optical fiber. You can see here in this formula, no dimensions are involved. It is only what it is, combination of refractive indices of n1 and n2 core and cladding. This is n1 square minus n2 square whole under root. That is a refractive index. So light gathering ability of optical fiber, it is defined in terms of acceptance angle. So sine of angle of acceptance is numerical aperture, and which is equals to under root n1 square minus n2 square, which gives us light gathering ability of the optical fiber. More is this Na, more is the light gathering ability of the optical fiber. Okay, so this is, we can also write this in terms of fractional refractive index change. If you give me a minute, I can do that for you, or if you have class, then we can discuss it tomorrow. So we'll discuss it tomorrow. Okay, if you have anything to ask, any confusions, you can ask your problems. And again, CR जो है वो मुझे अपना consolidated within, or you can by tomorrow, if you can do, you give me that consolidated attendance.
Thank you, sir.
Okay, beta, okay. You can hang up if you do not have anything to ask. I'll share PPTs with you. I'll share PPTs जब भी chapter एक level तक खत्म हो जाता है, I'll definitely share that with you.
सर आपने जो 4 केसेस बताए थे अभी,
हाँ बेटा,
तो सर वो फर्स्ट वाला ही क्यों हम यूज नहीं कर रहे, क्योंकि उसमें तो सबसे मिनिमम टाइम लग रहा है ना।
हाँ हो रहा है, उसके अलावा सभी में जा रहा है वही। अभी तभी मैंने कहा कि इट इज टू अर्ली टू कंक्लूड एनीथिंग। यू विल सी नंबर ऑफ थिंग्स हियर कि सिग्नल कैसे प्रोपेगेट होता है। जब हम सारी बात करेंगे तो ये एक सिंगल मोड ऑप्टिकल फाइबर भी होता है, उसमें सिर्फ एक्सिस के अराउंड यही सिंगल मोड जो आप देख पा रहे हैं। यू आर टॉकिंग अबाउट सिंगल मोड प्रोपेगेशन। सो वी हैव डिफरेंट मोड्स ऑफ प्रोपेगेटिंग लाइट थ्रू द ऑप्टिकल फाइबर, है ना। तो उस मोड्स में हम पढ़ेंगे, सिंगल मोड भी है जो आप कह रहे हैं, यस दैट इज आल्सो देयर। वहां पे डिस्पर्शंस भी कम हो जाएंगे, बट लाइट गैदरिंग एबिलिटी रिड्यूस हो जाता है, और we'll discuss that in more detail, है ना। वो आना है, that is part of our discussion, coming discussion.
ओके सर।
सर एन नोड कहाँ चला गया सर, वहाँ पे थोड़ा डाउट है।
एन नॉट जो है वो एयर का रिफ्लेक्टिव इंडेक्स हमने लिया, और वैक्यूम और एयर में हम स्पीड ऑफ लाइट में बहुत ज्यादा चेंज नहीं मानते, इसलिए we take that equals to 1 because 3 into 10 raised to the power 8 meter per second divided by, तो वो that gives you मतलब n naught and divided by velocity of light in air, ठीक है ना। तो that comes out to be approximately both are same, so that's why we treat it 1.
यस सर, थैंक यू सर।
Excuse me, sir.
हाँ जी।
Sir, what is the meaning of numeric aperture? As you said, it is root n1 square minus n2 square.
हाँ, it is name given to this parameter, and this is physically it means, or significance is what it gives you, light gathering ability of the optical fiber. Light gather कर रहा optical fiber, वो acceptance cone पे depend कर रहा है। Bigger is the acceptance cone means bigger light it can gather. Smaller is the acceptance cone, smaller will be the light gathering ability of the optical fiber. एंड acceptance angle किस पे डिपेंड कर रहा है? That depends on, you see that critical angle, that is phi c at the core cladding interface, or n1 and n2. So we have written it in terms of this theta a in terms of n1 and n2, and that gives you, it is name given to this parameter, numerical aperture, and this decides light gathering ability of the optical fiber, or measures the light gathering ability of the optical fiber.
Okay, sir.
Okay.
एक्सक्यूज मी सर
Yes.
सर cos phi c की वैल्यू अंडर रूट n1 स्क्वायर माइनस n2 स्क्वायर बाय n1 स्क्वायर कैसे आई सर?
अच्छा, एक सेकंड में स्लाइड फिर से स्क्रीन शेयर है मेरा. साइन स्क्वायर थीटा प्लस कॉस स्क्वायर थीटा इज इक्वल टू 1 वाला कॉन्सेप्ट हमने यूज किया.
सर इसमें ये जो n1 ये सर cos phi वाला cos phi c.
हाँ, वही मैं कह रहा हूँ. हमने क्या कहा कि साइन स्क्वायर फाई सी प्लस कॉस स्क्वायर फाई सी शुड बी इक्वल टू 1. ये तो आपको ट्रिग्नोमेट्रिक आइडेंटिटी पहले से मालूम है ना. तो इसी को हमने यूज किया और हमने कहा कि I can shift this sin square phi c to right hand side.
Yes,
I
sir.
can write it as 1 minus cos phi c is equals to, or cos phi c square is equals to 1 minus sin square phi c.
यस सर.
है ना. और फिर cos का स्क्वायर हटा देंगे तो it will be under root 1 minus sin square phi c.
यस सर.
ठीक है, क्लियर?
यस सर.
ओके.